address. All right, so this is a project that is hosted by the Department of Computer Science and Engineering. So to begin, I would like to welcome our friend Uday Kedkar to please come right and address all of you.
Very warm good morning to all of you. As Shivram said, it's always nice to come here. I recall having come. Problem with mic. I guess it's an indication that I should restrict my speech to very few words, which I will. So it's nice to see the enthusiasm, the passion and the creativity in the students all over the country, and I'm happy that IIT Bombay has been able to seed it, and I'm so happy that my colleague Kavi has initiated it, and now Shivram is taking over. Now we have Nived also here. It's always nice to go out of the institute and look at what other students are doing, what other colleges are doing, and there is so much of talent around. And as Shivram said, this is indeed the future of the country. I've gone through some of the details of the projects and they're really, really exciting. I wish you all very well. I wish you all the best, and I do hope that e-Yantra project will continue to inspire and excite young minds like this for many, many more years to come. Thank you very much.
As we do every year, welcome all of you. My name is Kavi Arya, PI of eYantra, been there for about 15 years. As Shivram said, I'm very proud that we've been able to find a very fine successor like Shivram. And I'll talk more about this tomorrow, but I think let's get going with everything today. So without much ado, I would invite our esteemed guests here to come and light the lamp in a very e-Yantra manner, and you'll see how it's done, right, using a bit of electronics. So would you please come, and Ajit will show you how to do it. Every year we refine the lamp a little bit. It's great. See, by word of introduction, I'd like to just introduce our guests here. First of all, Professor Hari Sahasrabudhe used to be the head of Department of Computer Science in IIT Kanpur many years ago, and he's been a big fan of eYantra, the project, and he's been a tremendous mentor and a fan of the work that we do. For a brief time, he also came as a visiting faculty 2002 to 2005 and helped us on the distance education program at IIT Bombay, of which I was a program coordinator. And out of that distance education program in 2002, which we began at IIT Bombay, trying to see how we can reach out to many more students and teach them engineering, e-Yantra is a product of that. Okay, so it's totally made in India. I keep on saying to everybody, it is to education in India what UPI is to financial payments in this country. Totally indigenous. We'll speak more about it tomorrow. Uday Khedkar is actually a student of Professor Sahasrabudhe, and we are very delighted to inform you that he's our head of department of computer science department, which incidentally is amongst the top 50 in the world, which is a huge achievement, because the other guys, I think us and, is it IIT Delhi? Around 40s mein hai, right? But they have the advantage that they have lots of foreign students and big grants and stuff like that, while we don't have those things, but we still are in the top 50, which is a huge achievement. Nived Chebrolu joined us from the University of Oxford. He's a core roboticist from the SLAM domain and stuff like that. He used to be at the Robotics Institute, so he's about 1 month old in the department, so you can stand up and take a bow, because you'll be seeing more of him as time goes on in e-Yantra. Okay. Parthiv Khound is also a colleague. If you can just take a bow. Right, he's one of your jury members. And last but not least, it was challenging to find a successor, right, who's not bureaucratic, not autocratic, and has his heart in the right place. And I'm very proud to announce the new PI of e-Yantra, Professor Shivram Kalyanakrishnan. Big hand. So he's an expert in AI and reinforcement learning. So as we go along and as we go forward into the future, we see e-Yantra specializing more and more in automation and AI, which is what the country needs. And we'll speak more about this tomorrow. So without much ado, I'd like to hand the floor over to my colleagues here to conduct the session and to take things ahead from there. Jason. So Jason, big hand for him. Jason has been managing the e-Yantra Robotics Competition over the last year. And as we say in e-Yantra, if you join us as project staff, you work with us for 2 years and then you get into the MTech program of IIT Bombay. And then the world is your oyster. So Jason is one of those guys, and the entire project is run by the blue t-shirt guys here that you can see, right, all of them. And it just shows you that there's no limit to what young people can do, right? So over to Jason.
Hi, good morning everyone. So we'll be starting with Krishi Cobot and the Krishi Drone team. Drone team is currently here and the Cobot team is in the first floor. So I will hand it over to the team developers. They will be briefly introducing the judges, as well as there is a presentation followed by that. So yeah, I think we can start over that. But before that, let me tell you, as Kavi sir was saying, dear participants, like you have been working for the last 7 months, and as we were mentioning that there are a lot of you who have spent the sleepless nights for the solutions, and we have been also through that phase. So be comfortable and don't be nervous. And so all of your nervousness or the excitement that you're currently feeling is just your passion that is coming out. And if you are worried about the achievement, you have already achieved it by turning that complex ideas into a reality. So we can start off with Krishi Drone as well as Krishi Cobot right now. Yeah, hand it over to Arun.
Good morning to all. My name is Arun P. Madhu. I am the team lead of Drone. So before going into the theme presentation, let me introduce the judges we have here. So from IIT Bombay, we have two professors who have come as judges for us. So first, I welcome Professor Vivek Natarajan. He is an associate professor at SISCON since 2021. he has done his PhD in mechanical engineering from University of Illinois. His research interests are motion planning, inverse problem, adaptive control, multi-agent networks, and vibration control. So I heartfully invite you. And second, we have one more professor from IIT as our judge, Professor Rohit Nanavadi. So he has been a professor in the Department of Aerospace Engineering since 2024. He has done his PhD in Aerospace Engineering from IIT Bombay itself. His research interests are sensor management, intelligent informative path planning, cyber-physical systems, and active Bayesian inference for environmental mapping. Again, I welcome you to our event. Thank you, sir. We also have here Professor Kavi Arya, who is the founder of e-Yantra. I welcome him. We have Professor Shivaram Kalyanakrishnan. He is our current PI. I also welcome him to the event. And then we have Professor Nived, who has recently joined us, and he has been working with us at e-Yantra. I welcome Professor Nived also. Coming to the industry persons, we have two people from industry who are here to judge us for this drone team. Coincidentally, both of them are ex-e-Yantra team members. So first of all, I welcome Mr. Smith Kesaria. So he used to work with us in e-Yantra. He used to lead this same drone team for years. He has done his MTech in Systems and Control, and currently he works as a robotic engineer in a firm called Find. So I welcome Smith again to this event. And finally, Mr. Vishwanathan Iyer. He is also a part of e-Yantra and alumni of IIT Bombay. So he has done his MTech in electronic system here in IIT Bombay. He currently works as a system integration and validation engineer at Intel, and his expertise is in silicon validation, system integration, test automation, etc. I welcome Vishwanathan here to the event again. I can see all of the e-Yantra participants and others who we are invited to the event. I welcome all of you to this first KD Krishi Drone run. So thank you everyone. Okay, let me get on with the team presentation. So this is the Krishi Drone team. So the aim here is to design and implement a PAD on a LQR control to navigate a quadcopter autonomously through a gamified greenhouse environment, as you can see in front of you. You have to identify some infertile plants in this greenhouse and carry out biopesticide spraying and then return to the home base. So this is the aim of this team. Let's look into what are the learnings here. So here students are taught about the dynamics of a quadcopter, PID or LQR control, ROS2, some image processing and programming in Python or C++.
Yeah, sorry to interrupt. For KC team students, participants, you have to assemble in front of the arena. We are starting right now.
Yeah, continuing. The tools we have used for this are Swift. Swift is actually the in-house quadcopter built by e-Yantra. Then we have used OpenCV, Gazebo, ROS2, and finally Betaflight firmware. Let us come to the arena. So this is the arena of Krishi Drone in simulation. This is in Gazebo simulation. You can see a gamified greenhouse arena. And the right side you can see the overhead camera which is there in the Gazebo simulation. This is overhead camera view and the terminal where students are running the scripts. So we actually teach them to fly in the simulation and then later on we go on to hardware. So this is the hardware part. you can see an arena that students have built themselves. The same one you can see in front of you. And the right side is the overhead view. And this is the configuration for today. This is the configuration we will be flying. Now to the quadcopter that we have built in eYantra. This is called a Swift Pico. It has a circular visual marker on top, which is called a icon marker. It helps us to localize the drone using the overhead camera you can see on top of this. And it is controlled by the Betaflight firmware. Now let's watch a quick theme film of the
Dum dum.
Music, audio for the video.
sorry for the issue. You can anyway watch that. Yeah, so the quadcopter takes off. You can see it taking off from the home base. By an LED, then it navigates through the hoop. That yellow plant is the infected plant. So when it touches the protrusion, and another LED will blink. That signifies the spraying, biopesticide spraying. After spraying in the yeah, this is a very sped through run of the simulation in the gazebo simulation of the scene. So this is the aluminum foil which we have attached biopesticide for infected. Finally, we come to the scoring criteria. So the total score for this team consists of scorer score, which set by the team at eYantra, and the judges score. So this is the scoring formula. Here T is the total time, 250 is the time we give for the total run, T is the time taken by the participants in each run. PI means plant identification. If you identify the plant through the overhead camera, and if you successfully come and just hover above the infected plant, PI is counted. Then PS is spraying. If you make contact with that protrusion and make the LED blink, you have a point for precision spraying. And for collision, if you collide into the hoop or any other part of the arena, you get negative points, that is CP. If you land successfully on the home base, you get LD, which is landing points 100. And if you manage to complete the entire and identify everything correctly, do spraying and come land at the base without any collision, you get a bonus points of 100. So the judges scoring criteria is, judges can evaluate the theme based on the following topics. Quadcopter dynamics in control system, judges can ask about the PID or LQR control, whichever the theme has used, and some basics of image processing. And finally, we come to the credits. So the theme developers for this is myself, Arun P. Madhu, then Shakti Magender, and Joel Sibi. And a special thanks to Jason Jose, who is the lead of eYRC, and all of the eYantra teams, especially the inventory team and the office team. So the project, entire project, eYantra is funded by the Ministry of Education. I extend my thanks towards them. Then our founder, Professor Kavi Arya. then to our PI Professor Shivaram Kalyankrishnan, and finally Team e-Yantra, which makes everything possible. Yes, that's all of my presentation. Thank you everyone for coming. I hope you have a nice, memorable event here. So, yeah, that's all the presentation.
So for the jury members, especially the new ones like Rohit, so e-Yantra represents a totally scalable way of skilling large numbers of people. So we run the competition in 2 stages. Stage 1 is inside a simulator where they have to solve the problem, and stage 2 is using real drone kits we give from our side. Now most drones, as you know, in the market that you get, DJI and all sorts of others, they don't let you get control of the sensors and actuators. So e-Yantra's genius has been to manufacture our own drones and have you guys assemble it and build the drone control system and all that. So the knowledge that you acquire in the process is not toy knowledge. The knowledge is very real. And many people have done startups based on the skills that they've acquired. And I'm delighted, we just had a walk-in here, Muthu Vangaliyappan. Big hand for him. Our alumnus, come in front. So a little bit about Muthu Vangaliyappan, perhaps. Okay, or maybe we can speak about it tomorrow. He's a very successful roboticist with a company called Goat Robotics. His humble beginnings was with e-Yantra in 2012, where he came to the finals and the internship and all that. And after a 5-day workshop in entrepreneurship, he said, "Sir, I want to do startup." I said, "Certainly, but promise that you won't take up a job, right? You do higher degree or a startup." And he took up the challenge, worked with Bosch for a couple of years, and then he started his own company called Goat Robotics in Coimbatore, and very successful. In fact, 2 months ago, I was at a huge automation exhibition in Nesco in Goregaon, and amongst the biggest stalls there was Goat Robotics. So big hand. And I'm really grateful that our alumni feel so close to us that whenever we call them, they are here to inspire the kids, students, and show what they've done. And somebody else, last but not least, the co-founder originally of e-Yantra is Professor Kriti Ramamritam here, who's been one of the most cited computer scientists of the country, and a big hand to him. Kriti, why don't you stand up and take a bow? Big hand. In fact, when I was trying to find a motto or a slogan, I went to him. He's a big loss to the advertising world actually, because we came up with this tagline of e-Yantra, engineering a better tomorrow. I could never think of anything better than that. We are engineering a better tomorrow, not only for India, but I feel the world. So big hand. And Saraswati, Dr. Saraswati Kritivasan here, was one of our early managers who built the e-Yantra infrastructure. So please take a bow. Big hand to her. She's part of the original team. Right, we set the whole thing up, and amongst others, right, we'll welcome all the others, but I want to take the old guys into account. Vishwanath here, and Saurabh. Where is he? He's upstairs adjudicating, right? Okay, fine. So we are very happy to have these old timers with us, right, who've been a very important part of the e-Yantra journey. So without much ado, I'll hand the floor over to you guys. And, yeah. Yes, in case Uday needed to leave early, right, we thought we'll be kind, and we have a little hamper here. So we don't give these useless, plaques that you can keep on the wall. We give you food. Thank you. Yes. Thank you. You're giving the impression that I gave you this too, sir. Okay. Thank you very much. So over to you guys.
So we are going to set up the arena in the configuration I just showed before. All the participants be ready. And one more thing, as we have stated in the rule book, a valid run requires correct pesticide pickup and spraying. I hope everyone. So I will call the team one by one. Whenever I call the team ID, you have to come forward and So for the judges from e-Yantra side, I will announce a successful pickup of pesticide, identification and spraying. You can. Yeah, so I invite team ID 1129 from KPR Institute of Engineering and Technology to the stage for their run. Give them a round of applause. So the team will quickly set up the things and then we can start the run as soon as possible. Just for the both of the judges, the team ID is 1129. So while they set up, so we have 6 finalist team. This team has worked hard. Like they had initially done the same thing in a simulation as just we have seen before. So from the simulation, we usually take the top 50 best performing teams and we send them free hardware kits where they do the same thing they have practiced in simulation before, and then they go through different stages, and in the final stages the best performing 6 teams are selected. So these 6 teams are the best out of the country who have participated in the Krishi Drone. Yeah. So when I tell you, you can start the timer. Judges, I mean e-Yantra judges, internal judges. So when I tell, you start the timer. Okay. So initially they will do image processing to identify the infected plant. Then only the drone run will happen. When the drone starts only. So the timer started. One collision. Disarm please. Yeah. The first run there was one collision. The run is considered invalid since it went out of the bounds. Yeah, now the second run comes again, you have to reset the timer. Yeah, now the team will try for the second run. Team, when I say 1, 2, 3, you can start your drone and do liftoff. Are you ready to start? Yeah, someone from the team will explain what is happening.
Good morning to the respected judges and everyone present here. We are team KD 1 and 29 and I myself Navneet Krishnan, that is Gohul, that is Dharnis and that is Girisangarji. We are from KPR Institute of Technology and I like to thank my college, dear principal and our innovation officer Arivan sir for providing this opportunity. From our college there are 3 teams we are presenting. One is ours, there is other team. We 3 teams have participated because of their support of 6 months. They have provided enough time and which helped us a lot. That is how. And during the development of this project, we have faced several problems. Let me tell by one. First, we are in a simulation phase. When we shifted to the hardware phase, the drone was drifting. Example, when we are working software, there is no error, or it's like felt like everything was working good. But when it comes to hardware, we are facing a drift like there's a steady.
Judges, be ready. Yeah, the drone has lifted off successfully.
That's like a steady drift. For example, let us know, you can consider we are moving from point to point, but now it is accumulating and fixing the steady state error. Steady state error, it happens due to the disbalancing. That is the one thing we have learned. Other thing we have processed is, we also faced an issue where the drone will come to the plant and it will latch. At sometimes the aluminum foil is fixed into the plant. At the time what the
Okay, successful pesticide pickup.
Sometimes what it will happen means the circuit will catch the drone and it will be hard to fly. At the time the integral will be accumulated and it causes to fly to more height. We have fixed it using the clamping techniques, anti-wind up. These things we have implemented.
It has crossed the greenhouse loop.
Along with that, in order to find the infected
Successful
plants,
PA and successful PS.
in order to find the infected plants, first of all we use the ARCO marker and we have find the region of interest. With that we have used the HSV. Using that we have able to detect the number of yellow frames, yellow pixels in the plant, and we choose the top 2 in it. Based on that we have successfully able to detect the 2 infected plants, and that is how it's working. Also,
Again successful PA and PS and 1 collision.
Based on different lighting condition, it was the HSV tuning was changing. Once we come there, it was changed, and we have tuned it completely
The
in
drone
order to this
exited
place
the
and based on the
greenhouse.
lighting conditions.
The drone has successfully landed. Everyone. So congratulations team 1129 for your successful run. You may now proceed to the Viva section. You can exit through. Yeah, PA is 2, PS is 2, 1 collision and 1 landing. So pesticide pickup is just for considering a valid run. There is no scoring for that. So judges can proceed to Viva. At the same time, I will ask the next team to come and set things up. The second team is team ID 1305, also from KPR Institute of Engineering and Technology.
Myself Girisangarji from KPR IT. I'm a third year student, CSE student.
Myself Navneet Krishnan MB, I'm from CSE.
Myself, Tarnishri from KPIT. I am third year studying in CSC department.
Myself, Gokulas. I am from KPIT. I am currently pursuing third year CSC department.
So we'll start with the Viva. So I will go first. So I'm going to ask you something. Okay, so your first run. So what happened there? Like,
Actually, we have forgot to change the camera parameters. So it's just too bright to detect the icon marker on the top of the.
So you did not know where to go.
Yeah, that's the reason we went there.
Okay. Now in your the way you are running it, you go up and you drift for a long time. So what is the controller doing? What is the algorithm?
Yeah, like in real world, real hardware. So every drone spins in its own RPM. So it's not perfect enough. Yeah, it's not perfect enough to go steadily upwards if we give that 1500 like a neutral value in the throttle. So we have to figure out some things like using PID to tune that little bit drift to make our drone navigate the
So my question is, okay, how did you make it to drift at the same constant location? What were your PID?
Yeah, the integral term accumulates the error over the time and it winds up the error to the set point.
So are you saying that your integral term is what is driving your whole thing?
No, not like that. So the drone drift the integral term only corrects the drone drift in the roll and the pitch axis. So
okay.
For everything, P is also working, D is also working. So without the P and D, we can do the navigations.
And what were the gain values you chose?
Like
roughly
8. For the P term we go for 8 and for the D we gone for 11 and for I we have chosen 4.
And how did you tune these gains?
Yeah, first.
Okay.
By trial and error method we have.
So how do you choose? Do you first tune the K, then or just tune the I? Which one you tune first? You say trial and error.
First initially we tuned with P and D alone without I.
Okay.
And without P and D, with P and D the drone moves upwards. It goes heavy, not in a particular waypoint. It moves around. Sometimes it moves in towards large up and sometimes it moves towards 2 down.
Okay.
It jiggles too much, so oscillates too much, and we used I to correct, and it particularly holds in a particular set point.
Okay, and you said you had used anti-venom.
Yes.
So what is that?
Let's say that situation doesn't happen here. There are some situations the aluminum foil may stick into the circuit. At that case, the drone can't able to fly. At that time, there's a thing like that a single phase it will be more weightage. Like it will happen when there's a constant wind or like there is a weightage over. At that time, the integral will accumulate over the time and it will cause to a more high value. When the drone has finished at the point, the eye has not changed to the slower value. It will be very high. That will cause the drone to overshoot and it will cause it to fly to over distance. We have used the anti-wind-up techniques like clamping to fix it.
Okay. All right. Done.
I just had one question. So, while you were modeling your drone, did you consider any? So, your two primary controls to navigate in the XY plane was pitch and roll angle, right? So, did you consider any limits on those angles when you are testing initially? Could you pitch any amount? Could you roll any amount? What are the limits that you found?
Yeah, like for certain terms, in certain situations there may be overshooting happens. So we have limited our output FC, that is FC output to around 1700 something, like plus or minus 200. So it will clamp itself. So
There's a base value, sir. Like 1500 is required for the drone to arm. 1500 is the value that is required for the drone to arm. Like in order to, we have clamp like plus 150 minus 150. Like it can maximum, it can push up to only 1650.
That's the rotor speed
yeah,
you're talking about.
that's like controlling the speed, maximum speed. So don't overshoot or no.
So like it won't like control directly the motor speed. It will control the angle of the drone.
Huh.
Yeah.
So you try to limit the angle of the drones using the speed of the rotors themselves.
Yes.
Hello. So I'm sure the sensors might have a lot of noise. So how do you deal with those noise before it goes to the PID loop?
Yeah, first of all, we have used the passive filter, like low pass filter is the one we have used it for the Ycon. The Z-axis is the main, we have faced a lot of noise.
Okay, so how do you know that what frequency of the data is noise and other frequency is the real data, and you filter out that
Like
frequency?
we have used the alpha value in the low pass filter, and the low pass filter is used to filter like the high frequency values, like they will have a jerk on very top, and it will only take the flow frequencies. So we can eliminate the original value and we can eliminate the noise. The low pass filter is one which will help us.
Okay, any other ways you can play with the noise without the filter?
We can deal with that by using like outlier. So we can find very like anomaly signals with the more difference. Like we can calculate with the previous error. So we can just analyze if the difference is very big, the input is very noise. So we can just eliminate that.
Okay, thank you.
So the team is supposed to go to the ground floor seminar room number 2 for your exit interview. You can go. Sorry, seminar room number 1. Again, give them a big round of applause. Yeah, so the team that is going to perform now is team ID 1305. 1305. Yeah, so they have done their image processing and they have identified the infected plants during this Viva time. Now they will start their flying session. So the drone has had a successful liftoff.
So, hello everyone and good morning to all judges and my dear friends present here. So, myself Abhishek Nehru and he's my teammate Nitishwaran. So, I'm currently studying third year at KPR Institute of Engineering and Technology, Coimbatore, and he's also doing his postgraduate there. So, my task
Successful
in
pesticide
this,
pickup.
so my role in this competition was taking care of the simulation part during the first 3 months. So, and actually being a team of 2, we actually implemented many techniques by ourselves individually. So, and finally collaborated with the ideas and we found a solution for many things. And to come to the hardware part, we faced an D-term striking up during the initial whoring part, since initially the drone will be at the ground
1
and
PA and 1
the
PS.
will be at the maximum height of 20. So that time the D spikes up and it makes the drone go up and come down, which takes some amount of time. So actually we solved that problem during the run, and sometimes we face, due to lighting issues, several plants may not be detected. Means the green plants also may be detected as infected. So for that I did the green masking technique, so that all the green plants which appear to be
LT successful landing. that team has successfully completed their first run without any collision.
Thank you.
So they will get a bonus, one bonus. CP 0.
Yeah, sure.
So now the team will go for the second run. The best out of the two will be considered as their final score.
So thank you.
Time? 1. So now they are changing their battery. One interesting thing, so this entire navigation thing is managed by ROS2. We manage this using ROS2 action servers and clients. So the waypoints come actually initial image processing, they detect the infected plants, then they send those waypoints to a service. So when this in the action server, when the client queries the service for the waypoints, it gives the services, and the client gives each goal point to the server. The server script is where the PID or the LQR code runs. Then we get successful feedback also during the run whether it has reached its goal point or not. Once it reaches its goal point, the second goal position is sent. That's how it navigates through the entire arena. Yeah, we will go for the second run. So with the drone you can see one transmitter. That is a transmitter we connect to the laptop. The communication between the drone and the transmitter happens to express LRS. Yeah, we are ready to start the second run. So the drone has successfully lifted off. It's now coming to us the pesticide pickup station. Yeah, the pickup didn't happen. One PI, one PS. Yeah, the drone has landed, the run has ended. One photo. So the pesticide pickup actually didn't happen, so we'll consider this as an invalid run. Yeah, the run is invalid. Congratulations, team 1305. You can now go for the Viva. Give them a round of applause. So now I invite team ID 1771 from National NIT Varangal. So next team is team 1771. So during the Viva, the next team will set up, do their image processing, and will be ready for the run as soon as the Viva ends.
Hi everyone, myself Nitishwaran and this is my teammate Abhishek. We are from KPR College, Coimbatore. So to tell about this competition, we are participate. For simulation is very, in the stage we struggled a lot. We even don't know we would find this further. Then after making more, I'll tell one by one what are the troubleshoots I have done.
I
So when
think
it
we'll
comes
go
to
with questions first. Yeah, we'll go with questions and you can explain the problem. So what I observed was that compared to the previous team's run, your drone was relatively slow and stable, and it did not oscillate in your direction. So was it just by luck, or was it an approach that you had taken apart from just PID, which made the drone completely little stable?
Sir, actually it's a trade-off. When you go with smoother the drone, it is slower. We will neglect all kind of those yard drift and simulation.
So that is, your approach was just to go slower. That's it.
Steady was our approach. Maximum speed we can reach. That is a maximum PAD we could go.
Okay. And the second run, we saw that your pickup was not done correctly, and you still decided to proceed. So did you not have any feedbacks about the pickup being successful, and could you not just wait and retry there?
Actually, we should have done a retry there, but since we couldn't even stop at the middle of the run, we continued it. But if we increase time to be time of the pickup station, it would most of the time it will.
So you did not have any feedback about a successful pickup of the pesticide?
We didn't get any pickup. Like if we any radio transmitters in pesticide station, we could have confirmation of that. So since it is Arduino, we couldn't do that.
Okay.
So, like, what was the biggest challenge you faced while doing the tactical, right? Like, actually, when you started working on the drone after the simulation, and like, how did you overcome that?
The ideas which worked on simulation was not working under real time. Like items, we tried different 3 to 4 types of accumulations, with nothing worked on real time. Then we used normal accumulation. Actually, the major issue we facing was the wiring issue. That ground wire was very minimal cut there, which is not visible by seeing. So drone is really behaving. We are tuning for 2 to 3 days, 4 days. We have a question mark which would be a problem there. Then finally figured out that is a wire there. The full wire is not cut off, so it is draining more amps. So it is was affecting PID too. This is a major hardware troubleshoot we have done. Then in software troubleshoot we done like in ROS, action servers takes some extra milliseconds to pick up the set points. So if we find it out by logging the values, so after logging that, it drone when goes up, it always goes smoother every time.
So, how did you debug that issue? The server is taking more time. In ROS, like, what did you do?
Actually, sir, we when every time shooting up, we found something weird at the random runs. So something random, it could be, but it is constant, happening every time. So we planned, logged all the PID values in a CSV file, and we saw the difference, set points, errors, what happening there. And also we found another thing during the first run, there will be no previous error. Previous error will be a 0. Actually, DTEM should slow down the drone. But since there is no previous error, DTEM will act according to shoot up the drone on the first run itself. So we neglected the error minus previous error, DTEM to be 0 on the first iteration alone. So that is first run logic. That's for now.
Okay, thank you. Just a quick question. So, were you able to quantify how much noise your localization was giving you, the Vico marker based localization?
Actually, there is a big noise over there.
So, how did you actually try to adjust for that in your PID design? If yes, how?
We used a simple low pass filter. So, if any spikes, sudden spikes, it will reduce. So if you we don't go for a gone for a big Kalman filters like that kind of first because we didn't have make all things to at a time, so we used a simple low pass filter.
So do you change anything in your algorithm between your first run and your second run?
No,
then
actually,
how come the first run was smooth, the second run was smooth? So what changed?
Sometimes when the drone starts and go to the home period, all the motors, the signal going from ESC will be not even. Sometimes it will the motor will get some delay to run. That is a hardware. Side. So to face this issue, if the drone skips a home position and goes to the pesticide station by unknowingly or goes somewhere else, so if it got somewhere else, it will come to home station.
So it's a hardware issue is what you're saying?
Not all the time, sir, but maybe sometimes the MOSFET can send the delay in some time, like two motors will spin after a very few milliseconds, it can happen.
And did you do anything with regard to the dynamics modeling, quad auto dynamics? Did you do anything there?
We don't do any dynamics, sir. We do use all the same quadcopter.
No LQR.
Okay. Just we worked on a waypoint navigation algorithm, sir.
Okay. And in your algorithm, do you have it scheduled? For example, initially only go up, so only one PID is working. Do you do something like that?
Yes, sir. To going down, it will first go down and go in further. So
these are fixed time instances. Go up for so much time, go forward for so much time. Is it?
We use fixed times. If a waypoint is like the pesticide station is a mandatory, we should hover there. So if it is a mandatory, it will hover for 5 seconds. If a waypoint is skipped and it moving towards a goal, we will say you go towards a goal. Don't stop there. We will send goal and the next goal position too. If it is moving towards the next goal position, then we will move towards the next goal itself. We will skip that goal if it is not a mandatory.
All right, thank you.
Thank you, team. You can proceed to seminar room 1 in the ground floor for your exit interview. So the next team is team ID 1771. They have done their image processing and is going to start the run.
Good morning everyone. Good morning judges. I am Dhanwan. The one handling the drone is Vikas and the one on the computer. So we are third year mechanical engineering students from NIT Warangal. We have used a PID controller for our implementation.
Successful pesticide pickup.
We have 3 independent PID loops controlling each of the axes. And then the drone, when it passes through the hoop, there is a chance of losing Vico track. And it has actually passed very well through. whenever it passes through the hoop, since the hoop is blocking above the camera, so we lose tracking. So we are essentially flying blind through the hoop, and the system has to regain control after that.
One PI, one PS.
And now we are, unlike other like traditional approaches, we slightly modified our waypoint server. We didn't want to treat every waypoint the same way. Some waypoints like picking up the pesticide station, detecting the plants, those we used as target waypoints where we defined two parameters, dwell time and tolerance. So for target waypoints, we have a higher tolerance and a higher dwell time. And in between transit waypoints, we have a lower tolerance and lower dwell times. So right now the drone is trying to go to the second block. It initially got caught up in the first plant.
One collision, the runners in it. It's a valid one. When the so land LD is 0, bonus is 0, collision 1, CP 1. So now they will go for the second run. So for judges, if the drone crashes, you can stop the timer at that time.
So right now we are changing the battery, and changing the battery is slightly risky for us because every time a new battery is introduced, the system dynamics slightly changes. Sometimes with an older battery, the tune works really good. With a newer battery, it's very aggressive and it is little bouncy. So we're hoping this battery functions better. So actually our drone was not working yesterday until like 9 p.m. It didn't even stabilize at a waypoint. We had to essentially swap motors, propellers and everything. What happened was, before coming to the competition, we recognized that one of our propellers was slipping on the motor, and our tune was for that. And naively we swapped the motor, like the propeller for that motor, and that tune did not work. And after coming here, a motor was also behaving cranky, so we had to change a motor too. So actually this is running an older tune on the older version of the software. Our newer software was not actually working on this.
Yeah,
because
second run.
1, 2, 3, go.
Successful liftoff.
So initially when a waypoint changes, there is a sudden change in the error rate. So the PID functions erratically. What we tried to do was ramp the set points from set point A to set point B slowly. So every successive time step, it moves a little bit by little bit. But initially here there was some error, so it was wobbling. Other runs it functions better. I think we have hit our integral clamp, so the drone's dynamics is little forward. Our integral clamp is trying to pull it back, but since we have hit the clamp, it can't physically go any further. We are ending the run here.
Run ends. The team can proceed for the Viva. Thank you, team. The next team is team ID 2398. 2398, Government College of Engineering, Karad.
I'm Dhanwant, I'm third year mechanical engineering department.
And because I'm third year mechanical engineer at NIT Varangal.
I'm Varshit from third year mechanical engineering at NIT Varangal.
Hello. So I have two questions. First question is something that you said at the end, that you're trying to ramp from one set point to the other because currently implementing the PID was not working out for you. Now, do you think there is some disadvantages of ramping from waypoint A to waypoint B?
One is we assume the drone is already at waypoint A, but our software is going sequentially, so that is taken care of. I think that assumption is valid. Other than that, the drone might actually behave sluggish when doing that if we don't set the correct rates.
Okay, so then a follow-up question would be, does the drone know what set points it has already satisfied and what are yet to come when you are ramping?
The way it works is our controller only gets a single waypoint. Once it tells it has settled on the waypoint, it then gets the next waypoint. So it does not know the history or the future. It only knows a location after it has completed the run.
So what is the tolerance limit that you use to check, okay, I have reached my waypoint, now can I get the next one?
For the target waypoints, we have 0.8 decimeters, so 8 centimeters plus or minus. And for the transit waypoints, it was 1.5 decimeters, 15 centimeters plus or minus.
And what's the span of the drone?
I think it's approximately 10 centimeters. The Vicon data is actually noisy, so it even keeping it static varies from plus or minus 0.4 decimeters, so 4 centimeters.
Okay. So do you think 8 centimeter was a wise choice as a tolerance limit then?
We believe it was because it functioned really well for us.
A separate question, so about your vision algorithm. When you were doing your initial testing or development, you might not have all these cages and background and environmental parameters might be ideal. So how do you plan for it in terms of algorithmic design when you come and deploy it on a next sort of a competition stage?
We did not find any, it was not much of a problem when we were doing the image processing, because the yellow we were trying, we put a tolerance limit to find the yellow. So it only detects that even if there is a cage, the color is going to be different, so we're only going to find the yellow which we need.
I see there is some fruit might have yellow hues. So does your image capturing also filter that out? Or do you just map to already known target locations and then?
Before doing the image processing, we are going to crop out the area where the plants are going to be there. So that's going to be out of the picture. Only of the...
So with some prior information where the plants are,
yeah,
that's how you proceed.
Yes, sir.
You said there is something about sudden motion, and once you change the waypoint. Can you explain what you are referring to there?
When the waypoint suddenly changes from, say, the hover over the base station and the H landing mark to the next pesticide station, essentially it is balancing at that point, so error is almost close to zero. And then once it suddenly changes, the error becomes around 6 decimeters. And since we have a fairly big KP term and KD is also big, the KP suddenly tries to pull it and it pitches violently.
But do you not try reducing KP and work with that?
We tried that, but we wanted the drone to complete the run as quick as possible. So we felt a ramp set point with a higher KP term can complete it faster than a slower KP.
So in both your runs, you could see that there was some oscillations. It was always overshooting. So what were you doing there? What was happening?
So
did you face it during your trials also?
This tune that we are running here was actually tuned 2 weeks ago, and the drone has completely changed. And since we got it working only 9.
But my question is, I understand that, but I'm saying in your trial runs, did you again see overshoot?
Yesterday night.
Even before, when you were doing it earlier, or was it smooth?
Some trial runs were really smooth, unless we changed batteries.
Okay.
Yeah. Okay. Those kind of issues when there is overshoots, we tried different approaches to tuning from scratch. One was having very high KD term and then slowly increasing KP without a waypoint. So trying to like stabilize at any location. We don't want to, so KI prevents the drift. We just wanted it to stay stable and then we introduced KI. But yesterday night here, what we did was we made our KP term 0, entirely relied on KI term, so to find an initial hover. But that assumption only works if our if our initial equilibrium values are correct. But we found that the equilibrium values are major source of our problem, because if the equilibrium values are not off, 0 degree pitch does not mean 0 degree pitch. The PID is asymmetric. Forward it behaves a different way and backward it behaves a different way. Nice. So actually the new thing that we implemented that we didn't run here was, once it hovers at over the base station, we take the integral I term, we average it, the history over which it stabilized there, and then add it to the base values. So the rest of the run, the equilibrium values more or less nice.
All right, thanks.
So you mentioned about that changing the battery, changed the dynamics of the quadcopter, also something about the propeller was slipping and your tunes were adapted to that. So you know this fact now, that even though the kinematics more or less is same, there are 4 motors, all of them are same oriented, but small mass changes and slippages change your PID tune. So if given one more shot, what could you do to adapt to all of those changes, so that if tomorrow I bring a new battery which is not seen, you could still perform a better stability? So what can you think about to adapt to all of those variations which are out of our control?
We were initially thinking of modeling the system mathematically, and we even tried that. Since we had a Rosbach file, our intuition was we created the system dynamics equation, a transfer function, and then we ran it on the Rosbach file. And our initial thing was we tried to run a PS algorithm to converge on the constants for the simulator. But since the run is 180 seconds that we have, even like a 0.001 change in the constant value created like a very large drift over time. So the simulator that we could build would only be valid for maybe 1-2 seconds. And initially our thought was to use it while it was crossing through the hoop, where it is flying blind, predict the steps forward so that it does not act erratically. But that tune was always off, because we tried hovering it, giving it a step input to find the system dynamics. But after like giving the step input, the Viacom tracker loses tracking data once the drone moves faster. So we were only able to get like the data for 0.3 seconds, 11 tracking data.
Okay, one last question following up your statement that when the drone is moving under the hoop, it loses the Viacom track for some half a second or something like that. What is your approach? How do you deal with that? Because your entire feedback is gone. So does your controller rely on the past generated input, or does it do something else?
Right now, it relies on the past generated input. The modified version, we set it to equilibrium values, the correct equilibrium values we calibrated. Right now, it was just the previous
And that
value.
worked always?
The previous values did not work always, but the equilibrium values, when we set it to equilibrium values, worked always.
Okay, thanks.
So the team can proceed to seminar room 1 on ground floor for their exit interview. Now we have team ID 2398, sorry. Team ID 2398.
So hello everyone, myself Pratikvak. I am a third year IT student and she's my friend from third year IT. These are our that guy is Nishkarsh from second year electronics, and that guy is Mohit from second year electronics. So we are from Government College of Engineering, Karad. Yeah, myself Pratikvak. I am the team leader. So there is always some motor issue that comes. One motor sometimes doesn't rotate. That's the hardware issues.
we are facing a small issue with the motor. One motor is not rotating. Yeah.
The
Start.
drone has been armed now. Initially you will see that drone is slightly on low altitude, and then it tries to come to a hover point which is over that landing pad. After it stabilizes there, it will start following the waypoints. It is not reaching the desired altitude. I guess that's because the battery, sometimes the battery doesn't give us that much power. I guess we have to change our battery. Okay, let's wait if it comes up.
So run has ended. Yeah, first run ended. It was an invalid run. For internal scoring judges, here for this team, as soon as the drone start flying, you can start the time. Yeah, so they are when they are arming, one of the motors failed to initialize properly. It's a
very rarely, but sometimes it happens. Yeah, started. Yeah, the drone successfully lifted off. So fact, the drone weighs about 51 grams. The frame of the drone is designed in e-Yantra itself. All other components are shipped from China. We use a all-in-one flight controller which has ESCs, everything inbuilt into them. We use CRSF protocol for communication. I guess this will be our last one. Yeah, you can. Yeah.
stop the run or you want to continue? It's your choice to make.
I don't think it is going to complete the run.
Do you want to stop the run or do you want to continue the run? Yes or no?
Want to stop the run.
Yeah, you can stop the run. Run stop.
Run has stopped. Team can proceed on to the Viva. So I invite the next team, team ID 1332 from Loyola Icahn College of Engineering and Technology.
Yeah. Myself Pratik Wak. I am from third year IT.
Hello, my name is Mohit and I am from second year studying electronics and telecommunication.
I am Nishkarsh Fartare from second year electronics and telecommunication.
Hello, my name is Sejal Mane and I am from TYIT. Third year.
So, can you explain what happened?
Yeah, actually yesterday we ran our successful run 3 times, but today what is happening, the drone was not reaching its altitude, and I don't know why it was not reaching.
So the hardware you used yesterday and today is the same?
Yeah, of course.
And the algorithm is also the same?
Yeah.
Okay, can you see in your laptop, can you see what are the different IK, the integral gain, the signals, right? The error signals that you have, the error, the derivative signal, the integral, can you observe that?
Yeah, we can observe that.
And so what were you seeing?
It was like not reaching its altitude, and I don't know why it was not reaching.
That's a steady state error, correct?
Yeah, yes.
Okay, if it's a steady state error, what part of the controller should take care of it?
KI. Yeah.
Okay, so now do you have any threshold on what value the integral contribution
actually, we
is?
have kept our K term very small because it was increasing oscillations as well. So for that, we are giving it a direct P and D term normally. But what happens if it is giving a steady state error, and it normally gives because of the like if battery changes and some hardware issues. And
so your I was very small, is what you're saying?
Yeah.
Okay. Yeah.
The drone works in 2 stages. In the first stage, it kind of calibrates itself at the ground level. We give it raw throttle so that it bounces off here and there for some time. We use very low values of PID, and what it does, it tries to solve it initial drift. It goes here and there. So even if it goes like onto the left or right, it comes back to the home base station, and then it lifts off again. It lifts with the different PID values and then completes the mission.
Okay, so now which one failed? Because you're saying you have two modes. Initially you were drifting around, and then you have different PID gains. So the first part worked well.
Yeah, I think first part went well. I don't know what was we need to debug in the logs. What actually happened?
Yeah.
Yeah, we will actually go through the logs. What actually happened?
Yeah. What will you look for in the logs, and like say you had to re-implement it, right?
Our
So,
log shows
yeah.
the battery levels and errors that it was facing through.
So you anyways brought up the battery. So was the battery replaced from yesterday to today? Okay, so full voltage, everything was fine.
Yeah.
But before the takeoff, you had a view. You could see the battery levels, right? Before.
Yeah,
the
we can
takeoff.
see.
So you had that as part of your checklist to observe that.
Yeah.
I mean, during your development, did you face issues of that sort, right? How did you overcome it?
During development we faced lots of issue with the batteries as well, because as the drone proceeds through the run, the battery decreases, and on the same PWM values, the drone is giving like lower throttle, so its height is decreasing. Cascaded PID controller, which increase battery throttle slowly as the battery decreases.
So you had this initial phase of drifting. Why did you include that?
Yeah, that because like if that's because item. If we increase the item, the drone starts oscillating, and to reduce that, we are just trying to use P and D term. So
To
drones.
take off.
Yeah, no, like to take off, we are keeping our item very high so that it can correct its like roll and pitch axes, and then come to center and then take off vertically.
Okay, I see.
And when it takes off vertically, then the item is so small that it doesn't oscillate that much.
Okay. Now you also said depending on battery level you change the gains.
Yeah.
It is continuous?
No, on the battery level, we didn't change the gains. We change the gains based on time. Like initial 5 seconds, I is very high, then I become small, and
these are sudden changes you introduce.
Yeah, on the battery level, we are just increasing the base throttle.
Okay. Okay. All right.
Yeah. Yeah, the image processing was the easiest part. Hardest one was the tuning of the drone.
Yeah, so can you explain the algorithm where you identify the non-infected plants versus the infected plants? What is your approach?
So our image processing approach is first we detect the Oroco markers and then we find the compute the homography for perspective transformation. Then we crop the ROI region of interest for detecting the infected plants. Then we count the infected plants by applying a color masking on it, and then we count the infected pixels, and after applying some threshold we publish the infected
So
plant
basically
labels.
just color filtering, basically wherever you see yellow which is infected.
Color masking.
And how do you define some thresholds? Is it based on trial and error? And
Yeah.
it works across all the different
We
light
set
conditions?
the HSV values which handle the light conditions.
Okay.
Low or high.
So was this kind of a standard approach that the instructors had asked you to do, or was it something that you figured out by yourself using the HSV values?
No, it is means we just set the low yellow to high yellow color ranges, and because of yes, yes, some noises means because of some noise there is a problem in detecting, but by using the Gaussian blur algorithms filtering. we- Yes.
Okay, thank you.
Known location for your plants to filter out the background noise.
Yeah. For we made around 12 circular spots so that we could ignore all the other yellow things so that it doesn't confuse us here and there.
Let's say if you did not know where the actual plants were, then how would you approach the problem?
Then we
As
would
in if
have
you don't know the initial 12 markers, but you just have that yellow filtering logic, how would you modify it to reject the photo of the fruit basket?
for that we would use feature matching algorithm. To we will take out a sample, then we will use the feature matching algorithm for matching this specific part of the plant or these plants which are already placed in the arena. So we could match it and we can easily spot it.
Features on the plant are not static. The plant might grow, the plant might change shape, the leaf might fall. So those features are not necessarily static.
Thank you, team. You can proceed for the exit interview in ground floor seminar room 1. Yeah, the next team is team ID 1332. So team ID 1332. Judges, be ready. So that was the end of the run, first run. Now we go to the second run.
माइक लगा है बताओ।
Hello judges, I'm Dazzle Roger, 4th year EC from Noida Icon College of Engineering and Technology, and my teammate is Jones Rogan, he's from 4th year ECE. Today we had some struggles with the arming. It's mainly due to motor synchronization issues. If you just press it and get the drone to produce more thrust in the motor that's descending, most probably it will synchronize. And then we both did everything together. We would implement the same thing and then discuss over it, either combine our ideas or implement which is better.
One position, one CP. Successful pesticide pickup. Position 2, CP2, disarm, end of run. Thank you team, you can proceed for the Viva. Give them a round of applause.
They are placed so they couldn't come. I'm Dasulari Roger, 4th year EC from Lizard.
I'm Jones Rohan from 4th year EC Lizard.
So what is observing about your control algorithm is the moment you start for other teams, typically forward, it just went up, it is result. So you seem to be activating all the control actions simultaneously. You seem to be going diagonal. Is that right?
Yes, there was drift issues. We tried to mitigate it with increasing the base value or decreasing the base values of the roll. Sometimes it works.
But don't you think it would be better to get some lift first and then move on?
It's not our plan to go diagonally.
Okay.
The motor is getting desynced, so the motor runs slowly in the starting. So while take off, the lag causing the drone to go diagonally.
Okay. So how is your algorithm structured? You go up, over, and then you move forward. Okay.
You can see, try to correct by coming back and then it went to the pesticide.
Okay. And do you have same gains throughout the run?
Yeah, same.
You're not changing the gains.
We haven't blocked.
Okay.
So acknowledging that you faced some issues in the start, but as you also said that after some time the drone was able to stabilize and also do a pick up, and for some moment it looked stable, and then again it started to go in spiral and then deteriorated. So what is something that went bad over time after even fixing it for some time?
Okay, we had two PADs. One, it had a, one is for speed and one is for stability. The speed, we have implemented a speed PAD now. The stable PAD had an important issue. It would just overshoot and then come slowly back. We implemented a speedy PAD and it was running perfectly in the test runs.
So was it something that switches in between the run or something that you manually change between the runs?
Yeah, two install. Yeah.
So how do you decide which one to use? Like was it just dynamically throughout the run or you choose it before the run starts?
Actually, one is critically, this one is actually critically timed. Like goes fast and stay.
So that's good, right? That should be used then.
Yeah, we used that one yesterday. That flew. Like,
so yesterday it flew, today it did not. Okay.
We don't know what's the problem.
Okay.
First question is more like a design question. So when you are tuning your gains, how much sensitivity do you think the weight of the drone brings in? In other words, if the drone were heavier, do you think the tuning would be simpler? Or vice versa, if the drone is lighter, the drone tuning becomes a difficult job?
Lighter one makes that tune, but I guess it overshoots a lot. A lighter one, heavier one, you need to adjust the. I am talking only about the altitude parameter. The heavier ones need to correct with the item. The lighter one can go with the P and D terms.
Okay. Thank you.
Continuing on that question, right? So if you were given a choice to build your own drone, right, or to solve this problem, right, I mean around this, like what would be the recommendations or feedback that you would give, right, which would have made it easier for you to solve this problem? Like what changes would you wish you had or you would recommend? Yeah. Or the key pain points you faced, right? And like you wish this would be better or improved so they could solve it better.
We thought like instead of vision-based localization,
okay,
any of the localization techniques we can use.
So you faced the issues for image processing, like what was the
for
localization? Okay.
Yeah.
So to detect the marker on the drone where it is, and then help you to navigate.
Yeah.
So you wanted.
While moving faster, the motion blur caused the drone, the camera to not detect.
Okay. So you have to consider the limitation of that to decide your speed and stability, and then go ahead. Okay. Thank you.
All right. Thank you.
Yeah, you can proceed to ground floor, seminar room number 1. And now we finally come towards the last team, which is team ID 2173. Team ID 2173. Just ready?
So good morning one and all present here. I am Ram Pasi and he is my teammate Vedant Ravnu, and we both are from the Symbiosis Skills and Profession University Pune, and we both are from the third year mechatronics students. So for this theme our basic approach was LQI controller, and we are the only team which implemented this type of approach. The major motivation behind this was we were last year also into the finals but in a different theme, and for the drone team we saw that very few teams actually use an LQI based approach, so that's where we tried this approach.
Successful pesticide pickup.
So initially in the simulation stage, what we had done, we had an LQR model which worked absolutely well. But as we transitioned from the hardware to from software to the hardware, we saw that due to the decreasing battery voltage, the system dynamics became non-linear. So we switched to an LQI controller to compensate for the battery loss, and that's why we became stabilized.
One PI, one PS. One PI, one PS.
Successful landing. 0 position, CC 0, bonus 1. So the team will go for the second one.
123 seconds.
Yeah, team's ready for the second one.
3. Okay. Starting. 3, 2, 1. Start.
So the conversion is happening to a set of predefined waveforms which we have in our waveform service. And so we majorly have 3 important points, which is the pressure type station, which is either 1 or 2, but in the final configuration we have got this one. Then there are the plants, and then there is another plant P2. And basically there are 2 plantation blocks for which you have
Successful pesticide pickup.
for which we had to extract the images, and we have to process them, and we accordingly got the coordinates from them.
One PA, one PS. One PA, one PS. So the drone has sprayed the pesticides successfully exited the greenhouse and is trying to land. Trying to landed at the front. So LD1, bonus 1, no collisions. So give them a big round of applause. So you can proceed to the Viva. Yeah. So in between we had a team which didn't only lift up, they couldn't perform well. So this won't be evaluated, but we will give them a chance to do a run because one of their scripts failed to run. So we are giving them a chance.
So now I'm passing an ad from Podium Mechatronics.
And I am Vedant Raman. I am also from third year Mechatronics. And we are both from Symbiosis Skills and Professional University, Pune.
Okay. So the natural question is controller because you already said. Okay. So it appears you had 2 parts. The integral part for liftoff. So you did liftoff only using integral. How do you do the integral? Just liftoff part?
No, actually we implemented a ramp function. So it will basically ramp the throttle till the hover point, then the LQI controller starts, like takes over.
So the LQR is stabilizing, once it reaches the LQR is stabilizing that as a set point.
Yeah.
Okay, now there was a lot of oscillation whenever you had liftoff, right?
Yeah.
So what was that because of?
I think it was because of the camera setup. In our college, our height was less, so the base throttle we set for the LQR controller was less. So here it was more, which we require. So the integral term was doing all the oscillation.
Okay, so you ramp up to a set point, and is that sort of open loop? You just run it right there.
Yeah.
Okay, and then once you get there, you try to do closed loop there. Okay. And then you have once it gets the right height, you have a different controller for moving forward. LQR again.
We only have a LQI controller.
Okay, so you had 2 of both you had LQR for the other one as well.
In the simulation we had LQR.
Huh.
In the simulation, we had implemented LQR controller, but due to the challenges with the hardware, like I mentioned about the battery compensation, so we tried LQR, but it wasn't stabilizing that well. So that's why we implemented an LQI controller.
Okay, so now how did you get your LQR gains? You had a model?
Yeah, we
Okay,
modeled it.
so how did you get the model?
We were only told to model the translational dynamics and not the rotational dynamics. So since it was already handled by the FC.
Okay, so how did you model the translation dynamics?
So we used the Lagrange's mechanics.
Okay.
And like we now currently have 9 states, out of which it's X, Y, Z, the positions, the velocities, and the integrals.
Okay, and then how did you tune the I for it? So you LQR, you got the gains, and then you had an I on top of it separately.
Yeah, we augmented an I differently.
And how did you tune for that I gain?
Yeah, so basically it was part of the K matrix only. So we can observe how the I behaves. So like it's oscillating too much, then I is very large. So we had to tune it just enough so it will reach the set point stable.
So how did you tuning for your LQR?
Yeah, by observation and by observing the graphs. We use plot juggler also. So we wirelessly send graphs to the laptop and we can observe how much it's overshooting, what's the integral states.
So when you talk about tuning in LQR, what did you tune?
Q matrix.
Q, okay.
Yeah,
okay.
Q and R.
Okay, good, thanks.
Why do you think that a lot of your flights were relatively more stable than other runs? Is it purely because of the controller?
Yeah, I think. So because LQR is an optimal controller, so we find the optimal K matrix using the ARE equation, algebraic equation, and then by also tuning it, it is more stable.
So do you think, can we achieve the same performance using a PID?
I guess we could use it, but I guess it would need a lot of tuning. So we did not wanted to tune that much, so we implemented LQR.
How did you decide the trade-off between Q and R? As in, did you fix R and then go on heuristically changing Q?
Yeah, first
or
R
did you fix Q?
So first all R's were fixed, then we tried tuning the Q matrix. So as we got the result as we expected, then we started changing the cost for that, the R matrix.
Oh, okay, so usually, okay, what were the sort of reasoning behind choosing or changing R values?
So basically we wanted the throttle to be smooth. So for the throttle values of R, we made it slightly higher. So the penalty was slightly lower. So it will become smooth. And in pitch and roll, the R matrix was a lot stricter.
Okay, so you relaxed the way the throttle was spent, but not the pitch and roll angle.
Since we wanted to improve time also, so we had to make it strict.
Okay.
Okay, so as you said, this is more of an optimal controller, but the usual challenges of the battery being changed, the dynamics still getting changed, let's say motor changes, propeller changes. So can all of those still be solved using the LQR, or is there any still limitation in that? If I today give you a completely new drone, some other team's drone, and you keep your same tuning and same values, will it still fly?
No, we would have to tune it.
Okay, so what do you think are the limitations of even LQR, and what can you do to solve that also?
So the main limitation are the states. Like the controller here is running at 30 Hertz, which is like very high for an LQR, very low for an LQR. So, and we need proper states, like there should be less noise, and also the LQR must be linear. Like if we went out of the linear stage, then it can oscillate a lot. So that's why we implemented RAM function to just make it in the linear range. So that's one of the limitation.
Okay, and so when we asked the previous teams that how do you deal with the noises with PID, so since there was a problem of differentiator and the noise being amplified, how do you deal with noises here in LQR?
So we had used 2 basic filters. One was for position we had Butterworth, and for velocity we had EMA filters.
What is the second one?
EMA, estimated moving average filter.
Okay, so more or less both are low pass filters.
Yeah.
But we also tried an Kalman filter approach. like Kalman state estimator since we have our modeled. So we tried that, but it was like not very good. So like it may be our fault, but the noise was very large. So we went with basic Butterworth and EMA filter.
Okay, thanks.
We discussed about the lift off, right? So in the second run, while trying to end the run and land, right? What happened there?
The drone had yawed a bit. So as it yawed, the orientation, the axis got disaligned. So that is why it started circling around. So we had this.
So like how did you figure out that?
Like
what
it happened in our home locations also.
You have seen that
yeah,
before?
we had seen it.
So you,
yeah.
Okay. So okay, one more question then. For your final submissions, how many runs did you do approximately?
We took a lot of runs. but
How many hours or days you flew? Like
2 full days.
2 full days.
Yeah.
Okay. How much time you had from the problem statement?
48
you got?
hours.
48 hours, right? Since when you know the problem and then
Yeah.
you attempted your runs and you have seen. I mean, is there any new scenario you saw today? What did you didn't see in your
No.
during the development? You have seen all the things. That's the reason you could predict that quickly. That's the
Yeah.
problem. What caused it? Good.
So as he asked, how many runs did you do before submitting your best run? So today, if we ask any other team who is using a PID or traditional approach to run it 10 times, and we let's say usually have a failure rate of 70 to 80%, only 2 or 3 runs are successful. What do you think your LQR or LQI approach would change it, or you have a higher success rate in 10 runs, let's say?
I would say it could. The reason why we took more runs was our lighting wasn't like equalized everywhere. So we had disproportionate lighting due to which we had got Vicon misses.
So if I ask you to run 10 times, the failure rate would be similar. Like it will only run probably 2 or 3 times as a successful
Everything
run.
depends on lighting conditions. If lighting conditions are okay, it will definitely run 10 out of 10 times.
Okay, fine.
I'm listening to you carefully. See to what extent your courses in your BE program prepare you for eYantra. Because all of you seem to be struggling hard trying to figure out how to focus on some particular area that you have a lacuna in, and then figuring out that it's not enough. So did you have any strategy towards this problem, to solving this problem?
So to what extent did your courses, right, in your curriculum prepare you for this? What did you have to do outside of that to learn, right?
So we purely had only PID in our course. We had only PID based approaches in our course. So we had to learn LQR from base.
Okay. I mean, anything else? Learn the skills, right? The overall requirements of this competition.
Yeah. So one of the main thing was our course didn't teach us ROS to Ubuntu. So we had to learn from scratch. We had to reinstall Ubuntu 2-3 times. So it was a very very nice learning process.
Right. So continuing that discussion, you mentioned one of your key pain points, so what the rest of the things was fine, right? Was on the lighting condition.
Yeah.
So would you wish any improvements on that setup, right? If you were given a free hand, right? Like keep rest of the problem and other things may be similar. But what is that key recommendation or improvement you would suggest that if that were be there, then this problem could have been even better, or you could solve it for a real world scenario, right? You could solve that better. What would be that?
So I think the camera is one of the issue in this setup.
Okay.
So as you can see, the Vicon rate is also limited.
Okay.
So if we try to improve the rate of the states that we are getting, we can improve much better. And also we are getting only X, Y, and Z position. If we also get the angles, we can definitely model the full dynamics.
Angle using the camera?
Yeah.
And how would you say camera, we have high FPS cameras, right? Like if this is processing at 30, say I have 120 FPS camera, we put that, right? But still, how do you figure out the angle? Like what would you propose the change in the system to figure out that?
Like in case of Aruko, we can get the angles also.
Okay.
So if we implemented a similar approach, we can get angles also. Although it will be noisy, but we can work with that.
But you feel adding that would help you stabilize and make it better. Okay, thank you.
Thank you, team. You can go to seminar room number 1 on ground floor. We will have a chance for the team, but this won't be evaluated. Sorry, we are facing an arming issue. We'll let them restart. We'll try for 1 more minute and then we'll close them. So the drone has lifted off.
Okay, so
Pesticide pickup is done.
Okay, so last time what happened is our one file had a mistake, like when the terminal
One PA and PS. Second PA and PS. Successful landing. Give them a big round of applause. Good run, very good run. So it was unfortunate they couldn't do it during the formal run, but anyway, they did a very good job. So that concludes the team run for the KD team. I thank each and every one of the participants and all the audience here, and especially the judges who have taken their valuable time to come here and evaluate the students. So I hope this has been a memorable event for each and every one of you. Yeah, I hope we can see you next year also. Okay, so yeah, so now I will invite Professor Chivaram Kalyanakrishnan to give a token of appreciation to our judges. Judges,